before we go to the next slide, any question? Are we together?
Yes.
Okay. So an artificial neural network, it's a model inspired by a biological neural network. So how our brain works. Our brain sends signals. That's why sometimes you can get hurt in, maybe you've fallen and your leg got hurt. Then you're going to feel pain. It's because your leg has communicated to your brain that I'm hurt, and then now your brain responds to that hurt, then you feel pain. So a biological neuron is made up of billions and billions and billions of neurons, networks connected all together. They send signal all over your body, they communicate with the whole body, and so on. So an artificial neural network, it's like we are trying to copy how a biological neural network works. So one thing I want you guys to understand, even right now, there are also some things even doctors don't understand about how a brain works, because brain is such a complicated aspect. Today you might be viewing things like this, then something happens, then you change your perspective. We're able to learn, we're able to grow. It's a complicated part of our body, and that's why even people tell you how you think, how you view the world is going to affect how the world responds to you. A lot, because the brain is so important. So even for artificial neural network, there's also an aspect of black box. It works, but there's also some aspect of it that it's complex for even for us that are scientists to decipher. Yeah. So that's something you're going to meet over and over. But as long as you the more you learn, the more you're going to understand what I'm saying. So an artificial neural network is made up of layers, interconnected units called neurons, and it's inspired by the structure and function of human brain. So the way the human brain has neurons connected with each other, that's how our artificial neural network has artificial neurons connected to each other. Okay, so an artificial neural network can model complex relationships and pattern in data. So another thing, when you're training a deep learning model, it needs a lot of data. It can take even the most complicated form of data. It can take big data, structured and structured. It's like it can do a lot of stuff. So it can perform a lot of complex tasks, even as human beings, some of the tasks that we can't even do, Yeah. So deep learning can outperform other techniques if the size of data is large, and it is widely used in tasks like image classification, natural language processing, speech recognition, speech translation, etc. Oh, I think even for use cases, let me see if I have a pen. These are just like a few examples of how it's used. Even for image generation, those AI generated images, AI generated videos, it's all neural networks. Yeah, that's just an additional point. So it has this structure. It has an input layer. Let's say this is an input layer. This is where our input comes in. This is where the image comes in, the text comes in. Then we have hidden layers. They can be as many as you want them to be, but the more the hidden layer, the more complex the model is. And then we have an output layer, depending on what we want a model to do. So if your model has just one hidden layer, it's not a deep neural network, by the way. So a deep neural network has a lot of, when you're talking about deep neural network, it has a lot of layers. The layers it has having many layers is what makes it a deep network. So all these layers are connected to each other. Like, this is just a simple explanation of the structure. So it can be as many hidden layers as possible, and it's going to form the same connections. Each one will be connected to the other. So this is like a simple structure of, and then now we have our output depending on what you want it to do. So this is the input layer, this is the hidden layer, this is the output layer. So the input layer receives raw data, e.g. features like age, salary, pixel value, etc. It's like the raw data, our input. Then our hidden layers, they perform computations like using, we're going to learn more about this when we talk about weights, we talk about biases, we talk about activation functions. We're going to learn more about that because they're all part of a neural network. So the hidden layer performs a lot of computations. Let's say I'll still use an image recognition example. I can still, let's say I have a banana. So my input would be maybe some, okay, you want input an image as it is. There are some, what do we call them? I don't, what's a simple word? I don't want to say computations or, this is some manipulations that you're going to do it to the image to make it vector like. You're feeding it into input. Then my first hidden layer can learn maybe a banana is yellow. My second hidden layer can learn it's curved. My other hidden layer, so they perform those they learn different things in that data. So when it comes to output, then our model will have understood all the properties of a banana. So they perform different tasks depending on the tasks that we want our network to perform. Then we have the output layer, which produces the final results. Could be a classification, could be a prediction, could be a recognition, could be a speech generation, text generation, anything that you want to output. So each neuron receives input values, multiplies them by weights, adds a bias. As you can see, it's repeating weights, bias, applies an activation function. So this is the process. So you can still get the process even if you don't understand what a weight is or what a bias is. So we have our input, then it's being multiplied by weights. We're not the one setting the weights for our input. Our network is the one setting the weights. It adds a bias term, then it applies an activation function. So an activation function introduces non-linearity to the network, and then it passes the result to the next layer. So I can talk a little bit about activation function. So before, I think the first class we learned about the history of AI, the way we had like a lot of peaks and winters, not a lot, 2 winters since 1956. So one of the problem that might have contributed to the winter, not the entire problem, but it was a problem on these neural networks. It was called an XOR problem. So an XOR problem is realizing at that point we didn't have deep learning, by the way, but we had what do we call it? A perceptron. It's like a simple input. It's like let's say a one layer neural network. It only has one hidden layer. So people challenged it because it could not solve an nonlinear problem. An XOR problem, it's a nonlinear issue. So it could only deal with linear problems. Then now scientists worked on it, came learned a lot about it. Then we had activation functions. So activation functions, they introduce nonlinearity, which means now our network can be as flexible as possible. So I don't know if you're together. I hope I'm not speaking in complex terms. Are you together?
Yes.
So activation function introduces nonlinearity, then it passes the results to the next layer. So depending on how many layers you have, so the next layer is going to multiply by weights, add a bias, add and apply an activation functions. They can vary from layer to layer also. This also depends on what you want the model to do. So one thing I've insisted with teaching algorithms and everything, it depends with your data, it depends with what you want your data to do. So there's not like a one way fits all. I won't tell you this is the exact way to do, but I can tell you if you are doing an image classification, if you have this and this is what you're supposed to do. If you are doing this task, this is what. So it's going to be flexible depending on the type of task that you want to accomplish. So this is a biological neuron. This is how it is structured. Um, we don't need to get deep into this is biology. So, anyways, but you can see we have it has like some sort of connection and input, some connections and output. Okay, this is biologically this is how your neurons, the neurons in your brain look like. But as I said, there are billions and billions and billions of neurons which are interconnected. So at the end of the day, this layer communicates to the next layer, communicates to the next layer, and then we have our output. Maybe that's when you feel the pain. That's when you realize what I've been hurt, and so on. So now this is our artificial neuron. So we have our inputs. So let's say our input is x1, x2, x3. We're going to multiply the input with a weight. So one thing you also have to understand, it's all math. It's math behind the algorithm. So it's still the same as machine learning, but now we're multiplying it. Then we add a bias term, or I usually call it a bias term, but it's called bias. Add bias. Then apply activation function. Then this is the output of this layer. So this output of this layer becomes the input of the next layer. Okay. I want somebody to say, okay, okay. Are we together?
Yes.
Okay. So, how an artificial neural network works, we have forward propagation. So when data is input into the network, it passes through the network in the forward direction, from the input layer through the hidden layers to the output layer. This is called forward propagation. So some are just forward propagation network. From input layer, we're going to that's how that's the flow of data: input, hidden, output. So we have another aspect called linear transformation. Each neuron in a layer receives input which are multiplied by the weights associated with the connections. These products are summed together and the bias is added to the sum. So this is like the linear transformation. They have said the input of this layer the output of this layer becomes the input of the next layer. It's like some sort of linear transformation. Then we have an activation function. So the results of linear transformation, sorry guys. Yeah. So linear transformation is we are taking our input, we are multiplying it by bias, we are adding we are multiplying it by weights, we are adding a bias term. Then now that result we are multiplying it by with an activation function. Then when we pass it through an activation function, it introduces nonlinearity into the system, enabling the network to learn more complex patterns. So some popular activation functions, these are just some. We have this is called rectified linear equation function. This is a sigmoid function. This alternate. Now that I talk about, I think we should have a class on activation function. We have several. We have several. So the ReLU is the common one. ReLU and sigmoid. I think these two are the most common one. You are going to meet with them a lot. But then we have others which come handy in different tasks. Yeah, these are just examples of the activation functions. So they all work differently. For example, when you say a sigmoid function, mathematically, what is a sigmoid function? I don't want to talk to myself, so I want us to, even if it's a try and error, what is a sigmoid function mathematically? I think sigmoid functions were active when we were doing, even in high school, when we were constructing those graphs for the cosine, sine, the not so linear graphs. So basically, a sigmoid function it looks like this. Oh, that's not a good one. It's like an S, and then it starts from 0, passes through this y-axis at 0.5, then it ends at 1. So it's what I'm trying to say, it's just some math that has been manipulated into a way that a machine can use it to learn as much as it can from the data, learn pattern, identify patterns and everything. So it's not magic. Yeah, so that's it. At least we have several examples. So this is, you don't need to overcram the formulas. You just need to know when to use them. When should I use the sigmoid function? But if you want to like understand, like maybe deeply, you can still go and learn more about this activation